Hello everyone, welcome to our YouTube channel. So today we are going to discuss a very important chapter, thermodynamics. So in NEET we can expect three questions, 2 to 3 questions from this chapter. In the past 3-4 years, you may have seen that thermodynamics regularly 2 to 3 questions being regularly asked from this chapter. Okay, so let us start very quickly. We'll try to complete this chapter. So system and surrounding, the very first term we are going to discuss. I hope all you know what's a system and surrounding. Just quickly have a recap of it. Like here we have taken a beaker, and in this beaker we are now heating water. So this water here which is boiling here, this boiling water is what we call the system. Except this boiling water, remaining what other parts is there, that is surrounding. So the system and surrounding here you can see is separated by a boundary or a wall. So between system and surrounding, whatever the separation is there, the wall is there. This wall is again of two types. One here we will call it as an adiabatic wall. So adiabatic wall, and another one is the diathermic wall. So adiabatic wall is what? Adiabatic wall is the insulated wall. Insulating wall means no exchange of heat will take place. And diathermic wall is a general conducting wall, like here heat exchange can take place. Okay. So now the system further is divided into three types: open system, closed system, and isolated system. Open system, here mass exchange will take place, also energy exchange takes place. Closed system, only mass exchange won't take place here, only energy exchange will take place in case of closed system. Isolated system, neither mass nor energy, nothing exchange will take place. So here we can conclude the point that in closed system you can see mass exchange is not taking place, but since energy exchange is taking place, then it must have some conducting walls. Then that's for the reason only the heat exchange is taking place. Similarly, the isolated system, since heat energy is also not exchange is not taking place, so here we can say it must have that adiabatic walls between the system and surrounding. Okay, so now let us discuss another fundamental term in this, like thermal equilibrium. Okay, so thermal equilibrium, like here we can say that if two bodies had different temperatures and they are brought in contact with each other, then what will happen between them? Heat exchange will take place. They both try to attain a same temperature, they both try to have a common temperature. This is what we call thermal equilibrium. They try to go to a common temperature and then they achieve the state of thermal equilibrium. Okay, so now associated with this thermal equilibrium, here we have a topic called zeroth law of thermodynamics. Here the thermodynamic law will start here. Here in this diagram you can clearly see that B and A, in between B and A we have conducting walls. Because of this, heat exchange is taking place, and between A and C also conducting walls are there. Because of this, direct heat exchange is taking place. But between B and C, they are separated by this adiabatic wall. Here this red color wall which is there in between them is the adiabatic wall. So what will happen? So here, since A and B will try to achieve thermal equilibrium and A and C achieve thermal equilibrium, so with the passage of time B and C will also achieve thermal equilibrium. Okay, so this is what we call zeroth law of thermodynamics. So very simple thing this one. So I hope all you know this. Next is about thermodynamic coordinates. So these three basic coordinates we have: pressure, volume, and temperature. These three we determine it as the thermodynamic coordinate. Like for a given point in graph we represent it with x, y, z coordinates. Similarly, a gas is there, then the state of the gas will be represented, or the phase of the gas can be represented by this pressure, volume, and temperature coordinate. If any of these changes or any two of the changes, then the phase or the state of the gas may change. Okay, so this thermodynamic coordinate. Apart from these three, some other coordinates are also there, but in this chapter we'll be restrict ourselves with pressure, volume and temperature changes. Okay, so next is about different properties. We have extensive properties and intensive properties. So the properties which depend on the quantity of substance, these are our extensive properties. Extensive properties, like here you can say, like here some volume is there, some quantity of substance is there whose volume is V. Now if I make this quantity into two half, then each half will have a volume of V by 2. So volume got reduced. So here I can say that volume or mass, okay, these are what extensive properties. They will change with the quantity. If quantity is changed, they also get changed, but that does not depend on quantity of substance is the intensive property. So we have an example for intensive property, like density is there, okay, temperature, density, refractive index. These are some examples. Like you can take a drop of water or a beaker of water, so both will have the same density, that is 10 to the power 3 kg per meter cube. They won't change with the quantity of the substance. Okay, now we have path function and state function. This one is also quite important for further understanding of the chapter, one of the fundamental thing. So the quantities which depend on the path followed are called the path functions. Okay, these are called the path functions. So best example here we have work done. Work done is a path function. Like if a graph, if you see here pressure and volume graph, in this pressure and volume graph, initial point and final points let it be same, but two different routes we have changed a gas. So here W1 work is done, W2 work is done. So although they have initial and final position same, but since the paths are different, work done will be different in the case. So later on you will see where work done will be more, and how to calculate this work done exactly and how they depend on the path. But for the time being you can understand that work done is a path function. Similarly, which is independent of the path, here we call it as a state function. It only depend on initial position and final position, not on the path followed. Okay, so here we can say like pressure and volume graph is there, and 2 points you can take 1 and 2. So for two different paths we will have same change in internal energy, delta U will be same. For the two routes also different routes are there, but change in internal energy would be same because of the same initial point, common initial point and common final point, change in internal energy. So change in internal energy here is a best example of state function. Now regarding the sign convention we'll see here, which will be useful to understand further numerical point of view, mathematical point of view of this chapter. So heat supplied to the system, we consider this to be positive Q, positive heat, and heat taken or heat rejected from the system is negative Q. Similarly, work done by system, basically here this expansion will take place. This work done is considered to be positive work done. Work done on the system in case of compression, work done is negative. If temperature increases, then delta U here we consider positive. Temperature decreases means delta U is considered to be negative. Okay, sorry, this one is negative, minus delta U, negative in case of temperature decreases. So these sign convention you should be familiar with. So for further using while solving the numerical we can use. So here the very first time we are going to discuss regarding the work done, how much work is going to be, what's the formula of work done is going to come here. So here you can see that the gas molecules are there, and because of supply of heat energy these gas molecules are expanding, and this piston also expanded by a dx amount. Dx is the length, area of cross section is A. So here this gas molecule must apply a pressure P on this piston, that's why the piston is expanding. So here if we wish to find out work done, mechanical work done, we know this small work done, if you consider dW, will be force supplied into the small displacement dx. So in place of force here we can write down simply pressure into area into dx. Okay. Now in this term of area into change in this volume, sorry, change in this displacement, we can write down A into dx as dV. So here we got a formula of dW as P into dV, or this total work done, if you wish to find out, then you can simply do integration of P dV. So P dV will be the work done here, P dV will be the amount of work done, integration of P dV you can do, and the limits also you can substitute initial volume to final volume. Okay, if they have already mentioned the change in the volume, then you can also use work done as P into delta V. This formula also can be useful, P into delta V. So here I can draw two important conclusions, like if volume is constant, that will imply delta V value to be 0, so that will imply work done to be 0, and similarly if external pressure is 0, then also work done is 0. So these 2 points we can consider, and in these 2 circumstances we have work done to be 0. Other cases work done is not 0, other cases will have different values, but in whole thermodynamics most of these 2 cases only will be considering about work done value to be 0. Okay, so when we have this external force, external pressure is 0, that is in case of free expansion, or in case of volume is also constant, there we have this work done value to be 0. Okay, now let us go into the first law of thermodynamics. So it's a quite important topic, first law of thermodynamics. So listen very carefully, just a second. Okay, see here in first law of thermodynamics, what we are going to see is heat supply. So to a system, heat is supplied, let it be delta Q, and work done by the system delta W, and change in internal energy is delta U. So here any system is there, whatever heat you supply, like here you can consider this to be a piston, in this gas molecules are there, and you supply certain amount of heat to the system, then the piston will get expanded. That means some amount of work is done, and also the internal energy of the gases also increased. So we can create a mathematical relation as delta Q equals to delta W plus delta U. So whatever heat energy we supply, this heat energy is converted into doing some useful work, and also to increase the internal energy of the system. Okay, so this is what we call the first law of thermodynamics. So it's a quite important law, it is based on conservation of energy. We will see further different thermodynamic processes, there we will see how this first law of thermodynamics will be changing for each case. Okay, now let us discuss about indicator diagram. So indicator diagram is simply a graphical representation of how a gas molecule is behaving with a different change in its thermodynamic variables. So here basically most generally we will take pressure and volume. So here suppose you can see that from this state to this state a gas is moving from A to B. So here what can I conclude? I can conclude which process is going on if arrow mark is given like this. So you can clearly say that initial volume to final volume the gas has undergone an expansion process. So here if it is undergoing expansion process, the work done must have been positive. Okay, so here if you wish to actually find out the work done, so you can actually uh, find the work done by simply drawing the area under this line, like here this green shaded region which I have drawn here will simply represent you the work done, and more precisely I'll say this work done will be positive in nature, since here expansion process is going on. Okay, similarly, suppose further from B to C, now this is the C point, B to C, here it has changed. So from B to C, what's going on here? Volume is remaining constant, so I can say that from my previous knowledge, work done here will be 0. Again, now from C to D, it has gone like this way. Now if you'll see, then if you wish to find out the work done from C to D, then again this area under this shaded portion you have to find out. Okay, so the remaining area which is left over, this area is the net work done. This is the net work done. So that means here we can say that area under this triangle, area of the triangle ABC will give you the W net work done you can calculate. If they ask you to find work done in particular range, then you can find the area under that particular line, but total work done they ask you, then the complete net area you have to find out. And one more important concluding point I tell you, that here you see which cycle is going on here. Here you can see that clockwise cycle is going on. Clockwise cycle, for clockwise cycle, if the cycle is clockwise, then work done will be positive. If the the cycle is anti-clockwise, then the work done you have to take negative. Work done will be negative. Okay, these two important points you can remember whenever you have a clockwise cycle given or anti-clockwise cycle given. Okay, so also while dealing with this indicator diagram, I'll tell you a few more important caution points. Like they have mentioned suppose pressure and volume, so you should be careful regarding the units. Here the SI unit for volume should be in meter cube, and the SI unit of pressure should be in, just a minute, yes, SI unit of pressure should be in Newton per meter square. Okay, so whether they have given in these units or not, that you have to check. If they have given like volume, they have given in liters, then you need to convert into meter cube. Okay, we have this relation of 1 meter cube. What is the relation? 1 meter cube means 1000 liters. So that means 1 liter equals to, we'll get 10 to the power minus 3 meter cube. So these relationships are important, and also you should be very careful that whether in y-axis, whether in the y-axis they have given, like here in y-axis, and in x-axis whether they have given pressure or volumes respectively, or if they have changed, like in y-axis suppose, they have given volume, x-axis pressure, then you have to find out the area on this volume axis, not on the pressure axis. Okay, so that means here what I told you, this area calculation, that means your pressure should be present in y-axis, volume should present in x-axis. If they have changed the axis, then accordingly you have to find out the area lying above the volume axis, where the volume axis is there. That part you need to be very careful while doing the questions. We'll see some questions here based on this indicator diagram work done calculation. So here this first question you can see they have given work done by gas taken through this closed process ABCA. First of all, you see ABCA is a cyclic process here, and that too it is a clockwise cycle they have taken. So here only we need to find out the area, the net work done through this closed process they have asked. So half into base here we have 5 V naught minus 2 V naught into height here we have 5 P naught minus P naught. So half into 3 V naught into 4 P naught. So 12 P naught V naught by 2. So 6 P naught V naught will be the answer here. So first option will be the correct answer for this question. Next one is see, same way only you have to find out. So this question some students slightly have confusion regarding taking the radius here. See, you all know that here area only you have to find out. So area here is no, circle area is pi r square. Then for radius, what radius you should take? If you see this radius, this value, then it would be like p2 minus p1 by 2. Okay. Similarly, if you will take this as your radius, then this value will be like v2 minus v1 by 2. Okay. So here in this case, this pi r square, further you can write down like pi into r into r. Okay, one radius you take from pressure axis and one radius you take from volume axis, v2 minus v1 by 2, and another one like v2 minus v1 by 2. Okay, so you'll get pi by 4 into v2 minus v1 into v2 minus v1. So here the third option will be correct, pi by 4 into p2 minus v1 into v2 minus v1. Okay. Next, example 3 you see here, it's given a system is taken along the path AB as shown if the amount of heat given in this process are QA and QB. Okay, so in this process they have given heat is QA, and in this process they have given heat is QB, QA and QB, and change in internal energy is delta UA and its change in internal energy delta UB respectively. Okay, so one thing without seeing anything, I can say that since both A and B have in a common initial point and final points, so the change in internal energies must be same, delta UA must be equal to delta UB. Since we know change in internal energy is a state function, it only depends on initial and final state. Now we have to check which heat is more. So as per the first law of thermodynamics, heat is given by work done plus change in internal energy. Now this change in internal energy is same in both cases. So the one who will have more work done, there more heat need to be supplied. So here from the graph clearly you can see that area under A will be more than the area under B. So work done by A will be more than work done by B. Okay. So work done by A is more means, so you can say that here heat supplied by A would be more than heat supplied or heat that consumed by B. So QA is greater than QB and delta UA equal to UB. So fourth option here we are going to get is correct. Clear? This example, example 4 you can check. So in a thermodynamic process, pressure of a fixed mass of a gas is changed in such a manner that gas releases 20 joules of heat and 8 joules of work is done on the gas. Okay, so the initial internal energy of the gas was 30 joule, then the final internal energy, here they are asking to find the final internal energy, here they are asking. So here you can see that heat released they have given. Okay, so here heat released they have given, heat released Q, delta Q, here you can write down delta Q, how much they have given, minus, here we will write down minus 20 joule because heat is released they have given, and heat is released means 80 joule of work is done by the 80 joule of 8 joule of work is done. So delta W here also you can write down minus 8 joules. Okay, minus 8 joule work is done on the gas, so work is done on the system they have given, so minus 8 joule here we have written. Okay, negative signs, I hope you understood the sign which I have used here. Now from the first law of thermodynamics, here we can write down delta Q equals to delta U plus delta W. So here it clearly we can see that delta U value will be how much, minus 12 joule. Just by putting down the values I will get delta U equal to minus 12 joule. But in the question they have given that initial initial internal energy they have given, U initial they have given. So U initial they have given how much? 30 joules they have given as the U initial. So change in internal energy was minus 12 joule. So now present internal energy would be how much? U final will be simply U initial minus delta U. Okay, minus of means here you can write down final minus initial equals to here plus delta U, because we have no the relation UF minus UI equals to delta U. So plus sign I'll put here. So U final equals to U initial is how much you are having? U initial we are having 30 minus delta U is 12. So presently we'll have 18 joule. So option C will be correct here. 18 joule will be the right answer for. Okay, so now we are going to see some different thermodynamic processes. What are the different thermodynamic processes are there? So regarding different thermodynamic processes, you see basically common processes we have as first one is isobaric process. Here in isobaric process, all you know that from the name bar, here we have this pressure is constant. We will just first see there what are the distinguished properties of each processes. Next one is isochoric process. So in isochoric process, volume remains constant, so change in the volume delta V becomes 0. So if delta V becomes 0 here, it's a process where work done can also become 0. Since delta V is 0, previously we discussed work done formula P delta V. Next one is isothermal process, which is considered to be a slow process here. So delta T in this case remains 0 or temperature remains constant. So that's why here we say this delta T value is also 0. And last one is adiabatic process, a very fast process, no time for heat to being exchanged. So here delta Q is 0. So these are the specialities of these following processes here we discussed. Now let us discuss in detail regarding each of the processes further. Now this is the diagram or graph, we say indicator diagram or the graph for different type of processes. So this graph is very important. In NEET generally they ask you, like as the name I have given you 1 2 3 4, you have to just identify. Here first one you can see it's an isobaric process since the pressure remains constant. Fourth one here we have isochoric process since volume remains constant. So among these 2 and 3, second graph represents isothermal, third graph represents adiabatic relations. So further I will explain you why adiabatic graph is having more slope as compared to the isothermal graph. If you draw the slope here, then you will understand that the slope of adiabatic curve here, what angle we are getting, is obviously are going to get more angle than the isothermal curve. Further we will see some mathematical relationship as the chapter will proceed, then you will understand this why we have isothermal and adiabatic placed at different positions. Okay, so now we are going to implement this first law of thermodynamics to each of these processes and again rewrite the first law of thermodynamics individually for each process. So like here you know this is the first law of thermodynamics, we all know delta Q work done plus internal energy change. So for isobaric process, if you'll see here, we have this isobaric process, pressure is constant, so simply we can apply delta Q is work done delta U, and further in place of this work done only we have substituted is P delta V. So nothing much change in the equation you will observe. So only in place of work done you can replace with P delta V, and this equation you can use wherever necessary. Next, in case of isochoric process, you will see that delta V is 0. I have told you already that work done will be 0 in this case. So since work done is 0, here the Warden value will put 0 means in the first law of thermodynamics you will get delta Q equal to change in internal energy. Since no work is done, all the work will be utilized here, and here the utilized to increase the internal energy. So this internal energy here we term it as NCV delta T. I will further tell you how NCV delta T or what is CV, that we will see further in the next 5 minutes. We'll check how delta U is becoming equal to NCV delta T. Okay. Now for isothermal process, we have delta T value is 0, so temperature is constant. So as temperature is constant, delta U is 0. Why delta U will become 0? Because just now we discussed regarding the formula of delta U is as NCV delta T. So here delta T value will substitute 0 means delta U becomes 0, and whatever heat is applied, all the heat will be used to do some work. No internal energy change will take place. So this is how you can see that first law of thermodynamics has different forms or different expression in each of these processes. Okay. So now next one is adiabatic process. So in case of adiabatic process, you can see here that delta Q value is 0. Since we have delta Q value 0, again you can write down delta Q 0. That will give me further as work done equal to minus of delta U. So here work will be done in the expense of internal energy. Internal energy will get reduced. Okay. Now this one is also quite important, specific heat of a gas. So in the previous chapter in calorimetry, you have all know that Q is given by the formula of Q is equals to NCV delta T or NC delta T. So here this C is the specific heat, we term it as, or C equals to delta Q by N delta T, where N is the number of mole, or you can say it molar heat capacity. So for isothermal process, if you are considering for an isothermal process, here you can see for isothermal process we have delta T0. So just by substituting delta T0 you will get C value as infinite. Okay. Similarly for adiabatic process, delta Q value is 0. Simply you substitute delta Q0, C value will get 0. That means C value depends on the type of process which the thermodynamic process is going on. Based on that, the C value will change. Similarly for isochoric process, isobaric process, we have this C values, special values are there. So in case of isochoric process, volume is constant, so we call it as specific heat at constant volume, and Cp in case of isobaric process we call it as specific heat at constant pressure. So further we will see what are the relations between Cp and Cv. Here we are going to discuss. So in general, if you see, this Cp value is always greater than Cv value. Why? Because Cp is valid in case of constant pressure. Whenever pressure is constant, so in that case we apply the specific heat as Cp. So pressure is constant when work will be done, also internal energy also, change in internal energy also take place. But if you have constant volume, when volume is constant, so no work will be done, only heat is required to change in internal energy. So that means more heat is required in case of constant pressure as compared to constant volume. So here from the formula only you can say that since more heat is required in this specific heat at constant pressure, so here as the heat is utilized in doing work as well as changing the internal energy, so here we have the Cp value would be more. So you can generalize that Cp value is more than Cv value, and in fact we will see a relation now, that Mayer's relation, where we will find out exact relation between Cp and Cv. So here comes the Mayer's relation. So it's quite important relation, Mayer's relation. The proof also I have done for Mayer's relation. See, if you are doing that CV, if you are writing the expression for CV, we simply express it as CV equal to delta Q by N delta T, or we have as per the first law of thermodynamics, you can write down as delta Q equal to delta U plus delta W, but delta W is 0, so in case of constant volume, so that's why here we are getting a relation as delta U equals to N CV delta T. Okay, let us consider this as our equation number 1. Similarly, from the kinetic theory of gases, law of equipartition of energy, so internal energy or total internal energy of a gas molecule is given by U is equals to FRNT by 2. So this is the internal energy. So where we have studied in law of equipartition of energy that in each degree of freedom, uh, equal energy, that is half kBT amount of energy is utilized. So for total energy, if you find out, so it comes to be FRNT by 2. So if you take delta on both sides, so you'll get this expression as delta U is equal to FRN or constant, so delta T by 2. Now if you try to simply compare this equation 1 with equation number 2, then you'll find out that in place of this CV, okay, here in place of CV, here what we have, FR by 2 is the term which is replacing the CV by comparing these two, equation 1 and 2. So here I can conclude that CV is nothing but, here we have this is CV relation as FR by 2, where F is the degree of freedom. For monoatomic gases, diatomic gases, polyatomic gases, different degree of freedoms we have. So I'll tell you in a tabular form what are the different degrees of freedom. Okay, this is the CV relation we got. So further CP relation, if you want to find out, so CP, again the same formula we have, CP equal to dq by N dt. So further here you can write down dq equals to dw plus du, and here in case of du, again you can write down NCV delta T, and in place of what, then I have written P delta V, okay, or PdV. Now simply you divide this N dt to both the numerator terms. So here N and dt get cancelled. So you'll get Cp equal to Cv plus P dV by N dt. Now we know this relation Pv equal to nRT, taking derivative on both sides, P dV equal to nR dt, or R equal to, we are getting Pv by N dt. So in this term here we can replace with R, that is real gas constant. So here we have replaced, and here in this expression you can see that we are getting Cp minus Cv equal to R. This relation is the Mayer's relation, Cp minus Cv equals to R, or from here I have got a relation of Cp also. Cp, you can rearrange this equation and you can get Cp equal to F plus 2 by 2 into whole into R. So these two expressions are quite important regarding this Cv relation, and this Cp formula, both are quite important. Okay, so here these are the interrelated formulas we are going to get between Cp and Cv. The ratio of Cp and Cv, we term it as gamma. So now if you put the value of Cp and Cv and try to express in terms of degree of freedom, gamma in terms of degree of freedom, it would be gamma equals to 1 plus 2 by F, or further degree of freedom also you can relate like this, F equals to 2 by gamma minus 1, or this is the Cv expression we have in terms of gamma, and Cp expression in terms of gamma, Cp equal to gamma R by gamma minus 1. All the expressions are very important. You should at least write down 3 times these all expression without seeing 3 times. This continuous interrelations are quite important. So definitely you will get questions from thermodynamics, also kinetic theory of gases, regarding these interrelations, numerical based questions you will get. So here I have given regarding this different values, just a minute, yes. So different values you can see here for monoatomic gases, diatomic gases, and non-linear polyatomic or triatomic gases, degree of freedom values 3, 5 and 6. So respectively you know each formula, These gamma values are very important. Monoatomic gas 5 by 3, 7 by 5 for diatomic, polyatomic 4 by 3. Okay, decimal forms also you can remember for the gamma values for each of the types of gases. Okay, so now the mixture of different gases, different moles, also different, having different specific heats at constant volume. So CV mix, CP mix and degree of freedom mix, same formula only, N1 CV1 plus N2 CV2, like that, divided by number of moles you can do. So for CP mix and degree of freedom mix you can apply these formulas. Next is gamma mix. So for gamma mix you can write down as gamma is Cp by Cv. So gamma mix you can find out Cp mix by Cv mix, or gamma is, since 1 plus 2 by F, or gamma mix is 1 plus 2 by F mix relation you can use. Okay, now we'll go to the work done in different thermodynamic processes. So let us see here different work done in different thermodynamic processes. So here we have this first is isochoric process. It's a very simple one. Continuously we are discussing this, that work done will be 0 in this case. So no more discussion on it, as here work done will be 0. Isobaric process, pressure is constant, so you can use work done is P delta V or P into V2 minus V1. So P delta V we can further change, like we know PV is equals to nRT, so P delta V equal to nR delta T. So whenever necessary we can also use nR delta T as the work done expression. For isothermal process we have work done as work done equals to nRT ln V final by V initial, or we can take 2.303 nRT log V final by V initial, final volume by initial volume, or in terms of pressure if you want to express, then delta W work done equal to nRT into ln P initial by P final you have to substitute for isothermal process. See, isothermal process they will mention it as a slow process, so you should be always careful regarding this, whether they mentioned a slow process, that means an isothermal process. Next is adiabatic process. Here adiabatic process is a fast process. So in case of adiabatic process, what happens, delta Q, here we have change in internal energy, delta Q, change in heat exchange is 0. So since no heat exchanges takes place, so by the first law of thermodynamics, as we discussed here, work will be done in the expense of internal energy. So internal energy delta U, one and only one formula we have, and CV delta T. This formula you can use. So in place of CV we have R by gamma minus 1 expression. So here you can see they have substituted R by gamma minus 1. So this is the work done formula, work done equal to N into R into T1 minus T2 by gamma minus 1. Or again NR delta T you can use P1 V1 minus P2 V2 by gamma minus 1. This relation also you can use. Okay. So as we are converting now from PV equal to nRT, so P delta V equal to nR delta T. This relation we are substituting here. Now after this we have different adiabatic relations, like here you see for isothermal conditions we have like PV equals to always constant. This is for isothermal condition. Okay, this is valid for isothermal. Similarly for adiabatic processes we have PV to the power gamma is constant. Okay, so if you differentiate this expression, further, and if you write down dP by dV equals to minus gamma by P by V. So this is nothing but if you draw a pressure versus volume graph, so this will be simply the slope of pressure versus volume graph will be minus gamma P by V. Okay, so for pressure versus volume graph this will be the slope. Clear? So similarly further you can use relations like, I'll tell you what's important here. You can use like PV equals to nRT, and find the value of P from here. P equal to nRT by V, and you can substitute the P value over in this P and find out this volume and temperature relationship, pressure and temperature relation. So that relations are also quite important, like I have mentioned here. See, temperature and pressure relation, T to the power gamma by P to the power 1 minus gamma is constant. Similarly, temperature and volume relation, T to the power T into V to the power gamma minus 1 is constant. So based on this, numericals are also very important, so it can be asked based on these numericals. So lastly, here one important point we will discuss regarding the slope of adiabatic and isothermal process. So for isothermal process, we have slope will simply come as minus P by V, and slope of adiabatic curve will be minus gamma P by V. So here we have slope of adiabatic curve is higher. So in this two graph, if you will see, this one will be isothermal graph. So in case of expansion, here is going on, and this one will be adiabatic graph. This one will be adiabatic and isothermal. Okay. So similarly, if compression will be going on, like the graph will start from here. Okay. In this case, this will be your adiabatic, and this will be isothermal. Just they exchange their places in case of compression. Pressure and volume graph is there. Clear? So as the gamma value is greater than 1, so here we can say that the slope of adiabatic curve is more. Similarly, for in between monoatomic, diatomic, polyatomic and isothermal also, they can ask you based on the gamma, you can decide. So here you can clearly see that theta 1 angle is obviously greater than this theta 2 angle from here. So I am saying regarding the magnitude of slope, don't consider the sign here. Okay, clear? So here up to this thermodynamics part quick revision we have completed. Next is about numerical portions. So separately I'll make a separate video for numerical portions of thermodynamics, important and expected questions from thermodynamics. Okay, so for quick revision, quick formula revision, you can follow this video. Okay, thank you everyone.